In contrast to traditional shutter-based cameras, event cameras record asynchronous events, which are per-pixel changes in brightness. This results in high dynamic range, lack of motion blur, low latency, improved data bandwidth, and less power consumption. Event cameras have recently been applied to many computer vision problems. This includes optical flow estimation, video interpolation and deblurring, 3D pose estimation, geometry reconstruction, and many more. However, existing event-based 3D reconstruction approaches can recover only sparse, colorless point clouds of the scene. Such sparsity is a limiting factor in many cases, especially in computer vision and graphics, and it has not been addressed satisfactorily so far. The research question we address in this work is whether just an event stream from an event camera moving around the scene is sufficient to reconstruct a dense volumetric 3D representation of that static scene in the absence of RGB images. Accordingly, we propose the first approach for 3D consistent, dense and photorealistic novel view synthesis using just a single short color event stream as input, which we call EventNeRF and describe next. Note that even though we use only the event stream as input, our results are rendered in the RGB space. On the left, we have an input event stream. On the right, we have a volumetric scene model. To this end, we adopt neural radiance fields, or NeRF for short, which is the state-of-the-art coordinate-based volumetric 3D scene representation. So how do we connect these two modalities? We propose using the following equation, where the left side can be computed completely from the events, and the right side can be computed as the difference between two rendered views. Hence, we can compute the accumulated difference by summing up the polarities from the events. And we can compute a similar difference from a volumetric model by subtracting two rendered views and applying a biofilter. We supervise our model by comparing these two differences, making them converge to each other as the model is trained. If we just sample rays randomly, as in the traditional NeRF, the model will either converge slowly or not converge at all, due to the sparsity of events. Hence, we propose a corresponding ray sampling strategy, which allows training EventNeRF efficiently and consistently. First, we split the whole event stream into intervals. We pick a random one as the window end. And then, we need to choose the window length. We notice that using constant short windows results in poor propagation of high-level lighting, and using constant long windows often results in poor local detail. Hence, we sample the window length randomly as well. Now, in every event window, rays are sampled from the positions where at least one event happened. However, if sampling is limited to non-zero rays only, called positive sampling, information about pixels with no events will be ignored, which would degrade the results. Hence, we also apply negative sampling, which means that we sample 10% of the rays from every other pixel in the frame. This makes our method more robust to noise events, and leads to better reconstruction of the uniformly colored surfaces and thin structures. Now let us proceed to the experiments. As the baseline, we propose the following simple approach. We start with the event stream and run it through a frame-based reconstruction method, such as E2Vid, to obtain RGB frames that we can use to supervise a traditional NeRF. However, there are many drawbacks compared to purely event-based approaches such as ours. The asynchronous nature of events is ignored. Having to store all the reconstructed frames drives up disk and memory usage, and there's a limit on the window size and the total number of views due to the frame reconstruction method. Here we show performance on synthetic data. We show that our method completely outperforms E2Vid plus NeRF and can reconstruct a variety of view-dependent effects, thin structures, and complex geometry. We recorded all real data using the following setup. We placed the object on a vinyl turntable, rotating at constant speed, and recorded the rotating object with our event camera. Please note that the resolution of our event camera is only 346 by 260 pixels, so the predictions here are greatly upscaled. All our real sequences were recorded under low lighting conditions using only a 5-watt USB light. Here, we show the original simultaneous RGB frames of the event camera. For clarity, we tone map these frames when they are used in the rest of the video. Note that EventNeRF does not use this data and only uses the events. In the fake plant ensuing sequences, the model can reconstruct every stem and leaf of the plant and even the 1 pixel wide needle of the sewing machine. In the microphone sequence, it reconstructs even the mesh of the microphone, similarly to the synthetic case. In the Goatling and controller sequences, we also show handling of high dynamic range by reconstructing both the dark details in the controller and in the fur, and highlights in the glasses. In the cube and bottle sequences, we show that we can reconstruct sharp color details. In the chicken and dragon sequences, we show that EventNeRF recovers details in fuzzy, colorful materials as well. In the multimeter sequence, we show that the model can reconstruct view-dependent effects, such as specular highlights. As with the synthetic sequences, our EventNeRF significantly outperforms our baselines on real data. Replacing E2Vid with SSL E2Vid leads to even worse results, as SSL E2Vid doesn't support color, mostly uses only the information inside the event window, and its performance is usually bounded by E2Vid. We also compare against deblurNeRF, which is an RGB-based Nerf method designed specifically to handle blurry RGB frames. We perform this comparison by applying the method on the simultaneous RGB frames of our event camera and simulated blurry frames of synthetic sequences. Results show that our approach significantly outperforms deblurNeRF while only using events as input. This is expected, as deblurNeRF can only handle view-inconsistent blur. In contrast, our approach produces almost blur-free results. We now proceed to an ablation study. Using fixed, long windows instead of randomized window lengths results in loss of fine detail on the object and some minor artifacts and trails. Disabling negative sampling results in significant artifacts. Now we discuss data efficiency. By varying the event generation threshold, we can control how much data there is without changing the duration of the event stream. Note that at thresholds high enough, some details never trigger a single event and hence cannot be reconstructed. As we can see, our model successfully reconstructs the scene even from 3% of the data, which is equivalent to less than 1 regular RGB view. This is possible because even this small amount of data contains all the information from all of the camera movement. Hence, we can still use multi-view consistency to reconstruct the scene. As our model is based on Nerf, we can apply marching cubes to its density volume to extract the textured mesh. Thus, our method can be used to reconstruct detailed textured 3D meshes of the objects. Also, our EventNeRF approach is not bound to a particular volumetric representation. To show this, we replace our original Nerf++ backbone with Torch NGP, and as a result, this model can be trained in just 1 minute and then rendered in real time on a single consumer GPU. We believe that this makes our method future-proof and opens up many exciting applications. For example, fast object scanning and reconstruction, which can be used on the factory floor. Object recording only takes a second, and reconstruction takes just a minute. We are going to publicly release our code and data in the near future. Thanks for watching.